All right, we're going to go ahead and solve this truss problem here. I noticed that it is got 1, 2, 3 joints, and it's got 3 members. Each one of these legs here of this right triangle is 3 feet, so it's a 45, 45, 90 right triangle. And I have a 50-pound applied load at joint C acting downward. I also have a roller at joint A and a pin connection at joint B. So one of the first things we're going to do when we solve a truss problem is we're going to draw the free body diagram. Drawing the free body diagram is pretty much as straightforward as just redrawing the truss, what you see, and replacing the supports, the pin and the roller, with reaction forces. And that's pretty much it. So I'm going to redraw what I see. I've got my right triangle here. Not the best triangle, but it'll work for what I'm doing. So this is joint A. This is joint B. This is joint C. I have that 50-pound force acting downward. I know that this is a 90-degree angle. The 2 legs of my triangle are each 3 feet. And I can assume that that's a 90-degree angle. We're not explicitly told that it is. However, because the 2 3 feet legs, one would assume that it's a 45, 45, 90, or conclude that it is. So this is what I have, but I also have my reaction forces. So because I have a roller supported on the vertical wall here, it's going to support horizontally, so it can push back. So I always assume positive directions for my reaction forces. So I'm going to have a reaction force. I'm going to assume that it's to the right. It's going to be called reaction force at joint A in the X direction. Now for my pin connection at joint B, I'm going to assume positive X and Y directions. A pin connection can support in both the X and Y directions. And so this is going to have a reaction force at joint B in the Y direction and a reaction force at joint B in the X direction. So there's my free body diagram. Next thing I'll do is I'll verify my static determinacy. The next thing we can do is go ahead and verify static determinacy. So I'm going to use the equation 2j equals m plus r, where j represents the number of joints. I have a total of 3 joints, A, B, and C. So that'll be 2 times 3. I have a total of 3 members because I have member AC, member AB, and member BC. So that is a total of 3 members. And I have a total of 3 potential reaction forces. Reaction force at A in the X direction, reaction force B in the X direction, reaction force B in the Y direction. So that's going to be 3. So 6 equals 6. So static determinacy tells me that I have enough equations to solve for my unknowns, and I have essentially a stable structure. Now what I can do is I can then move into my solving of my external forces. So that's my reaction forces. So I'm going to solve for my reaction forces by looking at my rotational equilibrium by taking the sum of the moment about the pin, setting that equal to 0, and then looking at translational equilibrium. In other words, the sum of the forces in the X has to be 0, and the sum of the forces in the Y has to be equal to 0. Okay? So now that I've got that done, or set up, let's go ahead and take a look at the first step here of solving reaction forces, which is the sum of I'm going to look at the sum of the moments about the pin connection, which in this case is A. And I'm going to treat that as my point of rotation. Correction, that's not my pin. My pin is actually at B. So B. Okay? So if I hold B as my pivot point, which forces will cause rotation about this point if I were to put those forces on my truss? So it was only supported here at this point. If I pushed with a force of unknown RAX at this point, and it was supported at B, meaning that the truss can swing freely around B, the truss would swing counterclockwise. And so RAX will cause that force will have a tendency to rotate the truss about that point. And so I'll say my moment there is RAX. That's my force. I need a distance, my perpendicular distance to that point of rotation. So that distance, if I focus on my line of action of this force, the line of action of this force is horizontal. So I should be looking for a vertical distance from that point of rotation, and that is 3 feet. So RAX times 3 feet is my moment, but my moment also needs a direction. And because that direction is counterclockwise, if I were to push at this point with a force of RAX and pivot it at B, this truss would swing counterclockwise, meaning that it's a positive moment. So I'll just put a little plus sign right here. All right. Now, the other force that'll cause rotation about point B, if I hold it here and allow this to swing freely, is this 50 pounds. If I push at point C downward, this truss will want to swing clockwise. So clockwise is a negative moment, so I'm going to subtract 50 pounds times a perpendicular distance. Now focus on the line of action of this force. The line of action of the force is vertical, which means I should be looking for a horizontal distance to my point of rotation, and that perpendicular distance is 3 feet. And so it's going to be 50 pounds times 3 feet, and that's going to be a negative moment. Now, those are the only two forces that'll cause rotation about point B, because if I look at these other two external forces on my truss, RBX and RBY, the distance to that pivot point B is 0. And if the distance is 0, moment equals force times distance, force times 0. Both of these will not cause moments. The distance is 0. So static equilibrium tells us that the sum of these moments should be equal to 0, and I can go ahead and solve that out. So let me go ahead and move the 50-pound term to the other side. So I'm going to add it to both sides, so that equals 50 pounds times 3 feet. And then I'm going to divide by 3 feet to isolate my unknown. And so RAX is equal to 50 pounds. Now, because I have a positive value here, my assumption for RAX is correct. It pushes back with a force of 50 pounds. So RAX over here is indeed 50 pounds. Now, that's step number 1 of solving for my reaction forces. My next step is going to solve for my translational equilibrium equations, and so I'm going to set up my sum of forces in the x direction equation. Anything to the right is positive. Now, according to my free body diagram, I have RAX going to the right plus RBX going to the right. And the other two forces, the 50-pound force and that RBY, those are in the y direction. So this is all I have in my equation. I can now substitute this RAX right here, and that was 50 pounds. And so RBX is equal to negative 50 pounds. Now, because this answer is negative, what that tells me is that my assumption for this direction of RBX is incorrect. RBX is actually going the opposite direction. So in the meantime, I'll go ahead and put a negative 50 pounds right here. That's going to tell me that it's not really going to the right, it's actually going to the left. And then my last equation is my sum of forces in the y direction. Sum of forces in the y direction. By convention, anything going up is positive. So I have RBY assumed to go up. The 50 pounds at joint C is going downward. Those are the only two forces in the y direction. Static equilibrium tells us the sum of that has to be 0. Therefore, RBY has to equal 50 pounds. My answer for this is positive, so my assumption of RBY going upward is correct. So that is, in fact, 50 pounds. So that's how I solve for the external forces on my truss. The next thing I'll have to do is solve for my internal forces. So what I'm going to do here is redraw my free body diagram and solve for my internal forces on my truss using something called method of joints. All right, so now that I've got this, I've got my external forces redrawn. I made a correction, so we found that RBX was really going to the left. So I went ahead and modified this so that it's really going to the left and it's a 50-pound force. Okay. What I don't keep anymore is I don't keep the negative because I've redrawn the direction of my force vector. What I'm going to do now is when I do method of joints, work through method of joints, let me go ahead and write some notes here. Method of joints. Oops, if I could spell correctly. All right. Method of joints. Couple things. One, we assume that all the members are under tension or compression. Initially, we're going to assume everything's tension, but we're not going to have any sort of torsion or anything like that, but we'll make an assumption that everything's under tension. We're going to assume that all my members are weightless, and we're also going to assume that all of my joints are frictionless. And what we're going to do is we're going to draw the free body diagram. So draw the free body diagram of a joint. And then we're going to go ahead and work through sum of forces in the X and sum of forces in the Y. So my translational equilibrium. Now, because I only have two equations, the maximum number of unknowns I could have at a joint is 2. Now, what I mean by that is that, for example, if we were to focus on joint C, which I need to label, and I draw the free body diagram for joint C, I would have member AC and member BC touching joint C. I don't know what the forces internally on these members are, so member BC and member AC are 2 unknowns. So at joint C, I have 1 and 2 unknowns, and then I know my 50 pounds going down, so I know that. But I have 2 unknowns. So I could start at joint C for this free body diagram, or for this method of joints rather. If I drew the free body diagram for joint A, I would have member AC touching joint A, and I don't know that. And I don't know the member AB that's touching joint A. But I know everything else. I know there's a reaction force here, and I know what that magnitude and direction is, so I know that. The only 2 missing pieces are the member AC and member AB forces. So I have 2 unknowns at joint A. At joint B, I also have 2 unknowns, the 2 members. But everything else I know. So really, I can start anywhere on this truss. For some trusses that have various orientations of different joints, you may not be able to start at every single joint. What I like about joint A in terms of B and C, so if you're trying to figure out, well, what joint do I start with? I like joint A because everything is 90 degrees. So I'm going to go ahead and just start off by circling all of my joints. And essentially what you see is what you draw for your free body diagram. So let's look at joint A really quick. What did I circle? So, oops, that's not what I want. So joint A. Okay, joint A looks like this. There's my joint. I have this 50-pound force to the right. Pushing from that roller connection. I have the force in member AC, and that is this force right here to the right. You see, I say draw what you see. I've got this force, I've got this force to the right, and I've got this force up. Now you draw the forces in the direction of the member like this. So this is the force in member AB. And we draw that direction because it's an assumption of tension. I mentioned how we're going to assume all of my members initially are in tension. So what I mean by that is this. If members AC is in tension, that means the member is being stretched apart. It is being pulled apart. Now, what is the member doing to the joint? This is a free body diagram of the joint. So what is this member AC doing to the joint? Well, if member AC is being stretched, what is it trying to do? It's trying to resist that, and so it's going to pull back. So it is pulling back in the direction of the member, and that's why this direction here is an assumption of tension. That's why this direction for AB is an assumption of tension. The member is being stretched, it's pulling back, trying to resist that. So the force it exerts on the joint is it's pulling back. Think of it as somebody came to pull on your arm and apply tension to it. Your natural reaction is to pull back. So what is the member doing to the joint? Well, it's pulling back. And that's why these arrows, these force vectors are in this direction. So now that I have that, I can go ahead and work through my equations. Sum of forces in the y direction, for example. Anything going up is positive. So I have the force in member AB, and I don't have anything else in the y direction. Static equilibrium tells us that the sum of the forces in either direction has to be 0. If that's the only force in my free body diagram, that tells me that this is 0. It has to be 0. There's nothing else in the y direction. What this tells me about the member AB is that it's a non-load-bearing member in these conditions. What do I mean by these conditions? If I apply a force of 50 pounds at joint C downward, and it's supported with a roller and a pin, then it doesn't take on any load. It is a non-load-bearing member. If I were to change up where I apply forces and the magnitudes and, make them go right or left at different joints, it may be load-bearing at some point, but in this situation, it's not. What about the sum of the forces in the x direction? Anything to the right is positive. I have FAC to the right, and I have 50 pounds to the right from that reaction force at A in the x direction. Static equilibrium tells us that it has to be equal to 0. So what this tells me is that the force in member AC has to equal negative 50 pounds. Now what this tells me is that the internal force on member AC is 50 pounds, and because I got a negative answer, that means it's compression. If I would have received a positive answer in method of joints, then my direction arrow, or my force vector direction to the right would be correct, and it'd be positive, and that would be an assumption of tension. But anytime you get a negative answer, your assumption of tension was incorrect, and it's really under compression. So now I know what the force in AB is, and I know the force in AC. So I've already got 2 of my members solved. I just need to solve for member BC. So I could either do joint B or joint C. It doesn't matter. I can go ahead and do joint C because it's got less. At joint B, I'm going to have 4 force vectors coming off of this joint, whereas in joint C, I'm only going to have 3. So what does joint C look like? I've got the force vector, or the joint, and I've got the force vector of the applied force going down, 50 pounds. I have the force in member AC going to the left. That's an assumption of tension. I know what FAC is. It's negative 50. Substituting that negative will correct my direction. So I'm not going to change up my force directions. I'm always going to follow the process of, here's my free body diagram. I have a force vector downward. I have a force vector to the left, and a force vector up and to the left. Okay, now this force vector up and to the left is this force in member BC. That's my unknown. Now it's at a 45-degree angle, meaning that if I were to break that up into components, this is what I would have. I would still have my force in member AC to the left. I would have this applied force straight down. I would have a component of BC to the left and a component of BC up. Now, because it's a 45-degree angle, sine and cosine of 45 degrees are the same. But based on where my 45 degrees is here, The horizontal component would be adjacent, and adjacent is going to be my cosine. So this x component of this force vector will be FBC times cosine of 45. And this will be FBC sine of 45. Now, where does that come from? Let's go ahead and go off to the side here. So here's my force vector FBC. It's got a 45-degree angle here. So if I want to solve for the x component and the y component, my y component, FBCy, and my x component, FBCx, what are the expressions for that? Well, if I write out my cosine equation, cosine of an angle 45 is equal to adjacent over hypotenuse. The adjacent side is that x component, FBC, and my hypotenuse is that force vector, FBC. So multiplying by FBC on both sides, I end up with FBC cosine of 45. That is equal to my x component. So going back over here, here's my x component, FBC cosine 45. How did I get FBC sine 45? Let's go back over to my triangle. That is the y component is my sine, or the opposite side. So sine of an angle theta, so sine of 45 is equal to opposite over hypotenuse. So my y component of my force vector over my force vector FBC. Multiplying by FBC on both sides, my y component FBC y is equal to FBC sine of 45. So that is where this y component came from right here. So at this point, it's just a matter of solving it out. I only have one unknown. That's my force in member BC. It's the only one I'm missing. Notice it shows up twice, FBC, FBC. I know what FAC is here, but I only need to solve it once. And so I'm going to go ahead and work the y equation. You could work the x equation if you want, but the sum of forces in the y, anything going up is positive, and that's my summation symbol. Came out kind of blobby. But anyway, let me go ahead and write this out. FBC sine 45 minus 50 pounds. Again, that's the applied force they gave us initially at joint C. Sum of my forces according to static equilibrium has to be 0. So FBC sine of 45 has to equal 50 pounds. Divide by sine of 45 on both sides. So FBC is equal to 70.7 pounds. The answer here is positive. Therefore, my assumption of tension is correct. So typically what I have my students do is I have them redraw the truss so that we've got members. We have our applied force down at 50 pounds. We know that we have a reaction force of 50 pounds to the right. We have a reaction force 50 pounds upward, a reaction force of 50 pounds to the left at that joint. And this is joint B. This is joint A. This is joint C. I also know that the force internally in member AB is 0. The force in member AC, that is 50 pounds in compression, so I'll put a little C. And then the force in member BC, we just found that to be 70.7 pounds, and that's in tension. And so there's my resolved truss, my final solution. Now you could check your work with something like MD Solids, so check out the video on MD Solids so you can see how you can set that up. But you can verify your work with MD Solids and find that it is in fact equal to those values. And so you see the MD solids results here, and you can see that the results match with what we just solved. All right, thank you.